Hello, in this lecture we'll find out the length of chord BC. In the drawing we have a semicircle. We know that the center of this semicircle is at this point, point O. Inside this semicircle we have square DEOF, and we know that the area of this square equals to 5 square units, and our mission is to find out the length of this chord called CB. Okay, so first of all we know that the angles, all the angles inside the square are right angles, therefore all those 4 angles are right angles. So write it down. This angle is a right angle. This angle is also a right angle. This is a right angle. And finally, this is also a right angle. So the area of square DEFO equals to 5 units. So DEFO, here the 2 squared brackets is the sign for the area. So the area of square DEFO equals to 5 square units. And we know that the area of any square equals to the side squared. So the area of square DEFO, that is equals to 5 square units, equals to one side squared. Okay, now we take a root out of this equation and we'll find out that the side, one side of square DEFO equals to square root of 5 units. So here all the sides of this square are equals to square root of 5 units. That is to say, DE equals to square root of 5 units, EO equals to square root of 5 units, FO equals to square root of 5 units, and finally FD, it is also equals to square root of 5 units. And in the next step we will join points D and O together by a straight line. Here, by joining points D and O, we actually created right triangle DFO. This right triangle, the green triangle is a right triangle because of the fact that angle DFO, this angle equals to 90 degrees, and DO is the hypotenuse of the right green triangle DFO. But DO, in addition, DO is also the radius of the semicircle. Why? Because point O is the center of the semicircle, as point E is the point on the semicircle itself. This is exactly the definition of a radius. Therefore, DO is the radius of the semicircle, and it is also the hypotenuse of the green right triangle DFO. So we will implement the Pythagoras theorem on the right green triangle DFO In this way we find out the length of the hypotenuse DO. Okay, so we focus on the right green triangle DFO. By PT. PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So I'll copy the right green triangle DFO in this page and we'll implement the Pythagoras theorem in the right green triangle DFO. This is the right triangle DFO that I copied from the original drawing. We have already found out that the length of DF equals to the square root of 5 units. It is one perpendicular. The other perpendicular FO, it is also equals to square root of 5 units. They are both the sides of the square DEFO. So according to the Pythagoras theorem, the square of the hypotenuse, that is to say, the hypotenuse is DO, and therefore the square of the hypotenuse is DO squared, equals to the sum of the squares of the perpendiculars. That is to say, it is equal to the square of the perpendicular DF, this is to say, it is DF squared plus the square of FO, plus FO squared. That is to say, it is the sum of the squares of the perpendiculars. DF squared plus FO squared. So DO squared equals to df squared. df equals to square root of 5 units. Therefore, df squared equals to square root of 5 squared plus fo squared. Fo, it is also equals to the square root of 5 units. Therefore, fo squared equals to square root of 5 squared. So I found out that DO square, that is the square of the hypotenuse, equals to square root of 5 units is 5 of course, plus square root of 5 units, this is 5. This is to say DO square equals to 5 plus 5, that is 10. We take out of this equation and we find out that DO equals to square root of 10 units. DO equals to the square root of 10 units. Here, we found out that DO equals to the square root of 10 units. That is to say, DO, that is the radius of the semicircle, equals to square root of 10 units. Here, point O is the center of the semicircle. Point A is the point on the semicircle itself. Therefore, AO is the radius of the semicircle, that is equal to square root of 10 units. Likewise, point O is the center of the semicircle. Point B is the point of the semicircle itself. Therefore, OB is the radius of the semicircle, that is equal to square root of 10 units. Okay. So, in the next step, I will present to you a new rule This is actually rule number 1. According to rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. I write it down. The sum of the angles on one side of a straight line is equal to 180 degrees. So actually, if we have a straight line here, AB is a straight line, and we have here this point is point K. So here, according to rule number 1, if we focus on the upper side of the straight line AB at point K, here the sum of the angles must be equal to 180 degrees. That is to say, the size of this angle plus the size of this angle, the sum of those two angles in total must be equal to 180 degrees. Okay, so this point is point L. That is to say, angle AKL, this angle, plus this angle, that is actually angle LKB, the sum of those two angles, in total, they must be equal to 180 degrees, according to this rule, rule number 1. The same thing is true if we focus on the lower side of the straight line AB at point K. The sum of this angle must be also equal to 180 degrees. Okay, so we can actually implement rule number 1 in our drawing. Why? Because in our drawing we have a semicircle, and we know that AB is the diameter of the semicircle. AB is the diameter of the semicircle. It is absolutely a straight line. Okay, AB is the straight line, so if we focus on the upper side of the straight line AB at point O, here the sum of those two angles must be equal to 180 degrees according to rule number 1. So which angles we have at the upper side of AB at point O? We have this angle that is equal to 90 degrees, plus the missing angle. In total, they must be equal to 180 degrees. So the missing angle must be equal to 90 degrees. In order to complete the sum of the angles at the upper side of the straight line AB at point O to 180 degrees, the missing angle here must be equal to 90 degrees. It is very simple. So actually here we have the pink right triangle EBO. We can actually implement the Pythagoras theorem on the pink right triangle EBO. So I copy the pink triangle in a new page and implement the Pythagoras theorem on this right triangle EOB. So this is the print right triangle EOB that I copied from the original drawing. We have already found out that EO equals to the square root of 5 units, and OB, that is the radius of the semicircle, equals to the square root of 10 units. So in the right triangle EOB, we will implement the Pythagoras theorem. Here PT is the expression for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is EB, therefore the square of the hypotenuse is EB squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EO squared plus OB squared. Okay, so EB squared, that is the square of the hypotenuse, must be equal to EO squared. EO equals to the square root of 5, therefore EO squared equals to the square root of 5 units, plus OB squared. OB equals to the square root of 10, therefore OB squared equals to the square root of 10 squared. In total, we found out that EB squared, that is the square of the hypotenuse, equals to the square root of 5 units squared, that is 5, plus the square root of 10 squared equals to 10. So in conclusion, we found out that EB squared equals to 5 plus 10, that is 15. Here we take out of this equation and we find out that EB, that is the hypotenuse, equals to the square root of 15 units. Here EB equals to the square root of 15 units. You can write down in the original drawing that EB equals to the square root of 15 units. Our mission is to find out the length of chord CB. We have already found out that EB equals to square root of 15 units. The only thing that is left to find, in order to find out the length of chord CB, is to find out the length of CE. In order to find out the length of line segment CE, we will make a construction. Actually, we will complete the semicircle to a circle. Here we completed the semicircle to a circle. In the next step, we will extend EO on both sides. We extend 9 EO on both sides, on the upper side and in the lower side. We extend OE by a straight line until it touches the circle. At this point, we define the touching point of the extended OE and the circle is point M. In the next step, we'll extend EO in the lower side by a straight line. And we'll define the touching point of the extended EO with the circle as point N. Here point O is the center of the circle. Point N is the point of the circle itself. This is exactly the definition of a radius. That is to say, ON is the radius of the circle and also the radius of the semicircle. We have already found out that the radius of the semicircle equals to the square root of 10 units. Likewise, point O is the center of the circle and the center of the semicircle. Also, point M is the point on the circle itself. Therefore, OM is the radius of the semicircle and the circle itself also. Therefore, OM equals to the square root of 10 units. And we have already found out that OE equals to the square root of 5 units. It is one side of square DEFO. Therefore, ME equals to MO minus EO. Again, ME equals to OM minus EO. That is to say, ME equals to OM, that is square root of 10 units, minus EO, that is equal to square root of 5 units. In conclusion, we found out that ME equals to the square root of 10 units minus square root of 5 units. And what is the length of EN? The length of EN equals to the square root of 10 units plus square root of 5 units. Again, EN equals to NO plus OE. That is to say, EN equals to the square root of 10 units plus square root of 5 units. In the next step, I will present to you a new rule, and rule number 2, and we will implement rule number 2 in our drawing. According to the new rule, rule number 2 is true in any circle. So this circle could be any circle. In any circle, if chord AB, this is chord AB, intersects with chord CD, this is chord CD, in the red line, and the intersection point of those two chords is at this point, point O. So I write it down. If chord AB intersects with chord CD at point O. Point O is the intersection point between the two chords. Then the following equation is true. AO times OB equals to CO times OD. I repeat again. If chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Okay, actually we can implement rule number 2 in our drawing. Why? Because in our drawing we have chord MN that intersects with chord CB at point E. Point E is the intersection point between those two chords. Therefore, according to rule number 2, we'll get that ME times EN equals to CE times EB. Again, ME times EN equals to CE times EB. So I'll copy the drawing again in a new page without the other fields here. And we'll implement rule number 2 in those two chords that intersect with each other. Chord MN passes through the center of the circle, that is to say, through point O. This is chord MN that intersects with chord CB and the intersection point between those two chords is at point E. Again, you can see here that chord MN intersects with chord CB at point E. So I write it down. Chord MN intersects with chord CB at point E. Therefore, according to rule number 2, ME times EN equals to CE times EB. According to rule number 2, we have already found out that ME equals to square root of 10 units minus square root of 5 units. We have already found out that EN equals to the square root of 10 units plus square root of 5 units. And we have already found out that EB equals to the square root of 15 units. And the only missing line segment is line segment CE. Okay, so we put the data inside the equation and we will find out the missing line segment CE. Here ME equals to square root of 10 minus square root of 5 times EN. EN equals to square root of 10 minus plus square root of 5, and it is equal to CE is the missing line segment times EB. EB equals to the square root of 15 units. Okay, so here square root of 10 plus square root of 5 times square root of 10 minus square root of 5, it is we'll find out the value of this expression according to the trigonometric identity that A minus B times A plus B equals to A squared minus B squared A equals to, in our specific expression, equals to the square root of 10 units, and B equals to the square root of 5 units. Therefore, if A equals to the square root of 10 units, then A squared equals to 10. A squared equals to 10 minus B squared. B equals to the square root of 5 units, therefore B squared equals to the square root of 5 squared, that is 5. In conclusion, I found out that A squared minus B squared equals to 10 minus 5, and it is equals to CE times square root of 15. 10 minus 5 is 5, so 5 equals to CE times square root of 15. We divide this equation by square root of 15, and we found out that CE, the missing line segment, equals to 5 over square root of 15 units. So we can write here that CE equals to 5 over square root of 15 units. What is the value of CB? It is very easy to see from the drawing that CB equals to CE plus EB. I write it down. CB, the chord that we are looking for, equals to CE plus EB. So CB equals to CE. We just right now found out that CB equals to 5 over square root of 15 plus EB. EB equals to the square root of 15 units. So the answer to the question is that the length of chord CB, you can see it in the original drawing, the length of chord CB, the chord that we are looking for, chord CB equals to 5 over square root of 15 units plus square root of 15 units. Here we can simplify this expression by multiplying square root of 15 by square root of 15, then we'll divide square root of 15 by square root of 15, so we actually multiply square root of 15 by 1, therefore we change nothing. So CB equals to 5 over square root of 15 plus, we'll multiply square root of 15 by square root of 15, and then we will divide it by square root of 15. So we found out that CB equals to 5 plus square root of 15 times square root of 15 over square root of 15. That is to say, CB equals to 5 plus square root of 15 times square root of 15 is 15 over square root of 15. That is to say, CB equals to 5 plus 15 is 20 over square root of 15. So here we will multiply CB by square root of 15, and then we will divide it by square root of 15 in order to eliminate the square root that is in the denominator. And we'll get that CB equals to 20 over square root of 15. We'll multiply this expression by square root of 15, and then we'll divide it by square root of 15. So here 20 over square root of 15 times square root of 15 over square root of 15. We multiply it by 1, therefore we change nothing. So CB equals to 20 times square root of 15. Square root of 15 times square root of 15 is 15. Here we will divide this expression by 5, both the numerator and the denominator, and we will get that CB equals to 20 over 5 is 4. So it is 4 times square root of 15 over 15. And we have to divide also the denominator of 15 by 5. 15 over 5 is 3. So in conclusion, we found out that the length of chord CB, the chord that we are looking for, equals to 4 times square root of 15 over 3 units. Or in terms of numbers, it is equal to 5.164 units. Okay, that is the answer to the question. I will verify it in the calculator. 4 over 3 times square root of 15 equals to 5.164 units. The length of chord CB, the chord that we are looking for, equals to either 4 over 3 times square root of 15 units, or in terms of numbers, it is equals to 5.164 units. In the next step, I will summarize the lecture. So in the original drawing, we had actually only a semicircle. We know that the center of the semicircle is at this point, point O. Inside the semicircle, we have square DEFO. We know that the area of this square equals to 5 square units, and our mission is to find out the length of chord CB. Okay. So first of all, we know that DEFO is a square, and we know that in any square all the angles inside any square are right angles, therefore those 4 angles are all right angles, are equal to 90 degrees. And we know that the area of square DEFO equals to 5 square units. And the area of any square equals to one side of the square squared. Okay? The area of square DEFO equals to one side of the square squared, and we know that the area equals to 5 square units, therefore we have the equation that 5 equals to side squared, the side of the square DEFO squared. Here we took a root out of this equation and we found out that one side of square DEFO equals to square root of 5 units. So we can write here that FO equals to OE equals to ED equals to DF, and they are all equals to square root of 5 units. Then we joined points D and O together by a straight line. In this way, by joining points D and O by a straight line, we created the green right triangle DFO. And we can easily find out the length of the hypotenuse DO, because we know that DF equals to the square root of 5 units and FO equals to the square root of 5 units. We implemented the Pythagoras theorem on the right green triangle DFO. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is DO, therefore the square of the hypotenuse is DO squared, and it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to DF squared plus FO squared. So in conclusion, we found out that according to the Pythagoras theorem, DO squared equals to DF squared plus FO squared. So DO squared equals to DF squared. DF equals to the square root of 5. Therefore, DF squared equals to the square root of 5 squared plus FO squared. FO equals to the square root of 5 units. Therefore, FO squared equals to the square root of 5 squared also. So DO squared equals to the square root of 5 squared is 5. So therefore DO squared equals to 5 plus 5. That is to say DO squared equals to 5 plus 5, that is 10. We took a root out of this equation and we found out that DO equals to the square root of 10 units. Here we can write down that the length of the hypotenuse DO equals to the square root of 10 units. So, and DO is not only the hypotenuse of the green triangle DFO, but it is also the radius of the semicircle. Why? Because of the fact that DO starts from point O, that is the center of the semicircle, and ends at point D, that is the point of the semicircle itself. This is exactly the definition of a radius. That is to say, DO is the radius of the semicircle, that is equal to square root of 10 units. For the same reason, OB, it is also the radius of the semicircle, therefore it is equal to square root of 10 units. Again, it starts from point O, that is the center of the semicircle, and ends at point B, that is the point of the semicircle itself. This is exactly the definition of a radius. And for the same reason, OA is also the radius of the semicircle, that is to say, therefore it is equal to the square root of 10 units. Okay? And then I presented to you a new rule number 1. According to rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. So if we have here the straight line AB, This is point K. We have here KL. If we focus on the upper side of the straight line AB, it's point K. The sum of the angles on the upper side of AB must be equal to 180 degrees according to this rule number 1. That is to say, angle AKL, this angle, plus angle LKB, in total the sum of those two angles must be equal to 180 degrees. The same thing is true, the sum of the angles in the lower side of AB are also equals to 180 degrees. That is to say, in the lower side of AB, this angle equals to 180 degrees. We can implement rule number 1 in our drawing. Why? Because in our drawing, we know that this is a semicircle, and AB is the diameter of the semicircle. We know that AB is the diameter of the semicircle. It is absolutely a straight line. AB is the straight line. And if we focus on the upper side of AB at point O, the sum of the angles must be equal to 180 degrees according to rule number 1. So which angles we have at the upper side of AB at point O? We have this angle, angle AOM, that is equal to 90 degrees, plus the missing angle, angle MOB. In total, the sum of those two angles must be equal to 180 degrees according to the rule. The sum of the angles on the upper side of AB must be equal to 180 degrees. Therefore, 90 degrees plus the missing angle in total must be equal to 180 degrees. Therefore, the missing angle must be equal to 90 degrees. That is to say, angle EOB equals to 90 degrees. This is a right angle, and because of the fact that this is a right angle, therefore the pink triangle EOB is a right angle. Therefore, we can implement the Pythagoras theorem on the pink right triangle EOB. So I copied triangle EOB in a new page, and we implemented the Pythagoras theorem on this right triangle EOB. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle is EB, therefore the square of the hypotenuse is EB squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EO squared plus OB squared. So in conclusion, according to the Pythagoras theorem, in the right triangle EOB, EB squared equals to EO squared plus OB squared. We know that EO equals to the square root of 5. Therefore, EO squared equals to the square root of 5 squared plus OB squared. OB equals to the square root of 10. Therefore, OB squared equals to the square root of 10 squared. In conclusion, we found out that EB squared equals to square root of 5 squared plus square root of 10 squared. That is to say, EB squared equals to square root of 5 squared equals to 5, of course, and square root of 10 squared equals to 10. In conclusion, we found out that EB squared equals to 5 plus 10. 5 plus 10 is 15. So we found out that EB squared equals to 15. We took out of this equation and found out that EB, the hypotenuse of this right triangle EOB, equals to the square root of 15 units. Okay, here EB equals to square root of 15 units. Our mission is to find out the length of chord CB. We have already found out that EB equals to the square root of 15 units. The only thing that is left to find, in order to find out the length of CB, is to find out the length of line segment CE. This line segment. In order to find out the length of line segment CE, we made a construction. We completed the semicircle to a circle. Then we extended OE in both sides. Okay, we extended OE in the upper side until It touches the circle at point M. Point M is the intersection point between the extended OE and the circle. Then we extended EO towards the lower side until it touches the circle. Define the touching point of the extended EO and the circle at point N. So point O is the center of the circle. Point N is the point of the circle itself. Therefore, this is exactly the definition of a radius. That is to say, ON is the radius of the semicircle and also the radius of the circle itself. Therefore, it is equal to square root of 10 units according to what we have already found out. Likewise, point O is the center of the semicircle and the circle itself. Point M is the point of the semicircle and the circle. Therefore, OM is the radius of the semicircle and the circle also. OM is the radius of the semicircle and the circle. OE equals to the square root of 5 units. Therefore, ME equals to OM minus OE. Again, ME equals to OM, OMO minus OE. Here, ME equals to OM minus EO. So, ME equals to OM, that is the radius of the circle and the semicircle. That is to say, it is equal to the square root of 10 units. Minus OE, it is equal to the square root of 5 units. Why? Because it is one side of square DE OF. So in conclusion, we found out that ME equals to the square root of 10 units minus square root of 5 units. And we also found out that ON equals to the square root of 10 units. Okay, in the next step I presented to you a new rule and implemented the new rule number 2 in our drawing. According to the new rule number 2, that is true in any circle. In any circle, if chord AB intersects with chord CD, the right line is called CD, and the intersection point between those two chords is at point O, then the following equation is true. AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. AO times OB equals to CO times OD. We can implement rule number 2 in our drawing. Why? Because in our drawing we have chord MN that intersects with chord MB at point E. Point E is the intersection point between the two chords. Therefore, according to, we can implement here rule number 2. According to rule number 2, we will get that ME times EN equals to CE times EB. Again, ME times EN equals to CE times EB. So I copied the circle with the two chords that intersect with each other in a new page. Here, chord MN intersects with chord CB at point E. Therefore, according to rule number 2, we'll get that ME times EB equals to CE times ME times EN. Again, ME times EN equals to CE times EB. We have already found out that ME equals to the square root of 10 minus square root of 5. We have already found out that EN equals to the square root of 10 plus square root of 5. Here. En equals to the square root of 10 plus square root of 5. And finally, we have already found out that EB equals to the square root of 15. Therefore, according to rule number 2, ME times EN equals to CE times EB. ME equals to square root of 10 minus square root of 5. En equals to square root of 10 plus square root of 5. And it is equal to CE, that is the missing 9 segment, plus EB equals to the square root of 15. We found out the value of this expression, square root of 10 plus square root of 5 times square root of 10 minus square root of 5, according to the algebraic identity, that A minus B times A plus B equals to A squared minus B squared. Okay? So here in our specific expression, a equals to the square root of 10, b equals to the square root of 5. So this expression equals to a squared minus b squared. A equals to the square root of 10 units, therefore a squared equals to 10. B equals to the square root of 5 units, therefore b squared equals to square root of 5 squared, that is 5. In conclusion, we found out that a squared minus b squared in our specific expression equals to 10 minus 5, and it is equals to CE times square root of 15. 10 minus 5 is 5, so we found out that 5 equals to CE times square root of 15. Here we divided this equation by square root of 15 and we found out that the missing line segment CE equals to 5 over square root of 15. Okay, our mission is to find out the length of CB. It is very easy to see from the drawing that CB equals to CE plus EB. Here, CB equals to CE plus EB. CB equals to CE plus EB. We already found out that C equals to 5 over square root of 15 and EB equals to the square root of 15. So the answer to the question is that the length of chord CB is chord CB. It is equals to 5 over square root of 15 plus square root of 15. We actually simplified this expression by multiplying square root of 15 by square root of 15, and then we divided by square root of 15, we multiplied by 1, so we change nothing. So it is 5 over square root of 15 plus square root of 15 times square root of 15 over square root of 15. We found out that CB equals to 5, and square root of 15 times square root of 15 is 15 over square root of 15. 5 plus 15 is 20. So in conclusion, we found out that CB equals to 20 over square root of 15. We want to eliminate the square root in the denominator, so we multiplied this expression by square root of 15, and then we divided by square root of 15. We multiplied by 1, so we change nothing. Okay? Here CB equals to 20 over square root of 15. We multiply 20 over square root of 15 by square root of 15. Then we divide it by square root of 15. So in the numerator we have CB equals to 20 times square root of 15. In the denominator we have square root of 15 times square root of 15 is 15. Then we divided both the numerator and the denominator of this expression by 5. Here 20 over 5 is 4, 15 over 5 is 3. So in conclusion we found out that CB equals to either 5 times square root of 15 over 3 units, or in terms of numbers it is equal to 5.164 units. I repeat again that the length of the chord that we are looking for, chord CB, equals to either 4 times square root of 15 over 3 units, or in terms of numbers, CB, the length of chord CB equals to 5.164 units. Okay, thank you very much.